going to put dog food into tins with a volume of 128 pi, and we need to work out the radius and height, which is going to give the minimum surface area of steel. We have the surface area of a cylinder, 2 pi r squared, two of those, plus 2 pi r h, the strip of metal that goes between the two lids. And we know that the volume of a cylinder is pi r squared h from secondary school geometry. So we want to eliminate h. We don't want two variables here in the function that we're going to differentiate. So we take the volume, we equate it to this, and from that we extract an expression for h in terms of r, 128 divided by r squared. This allows us then to write down the function that we are going to differentiate. So what we're going to differentiate then is that the surface area is equal to 2 pi r squared plus 2 pi r, and the h is replaced by this, so times 128 over r squared. We can eliminate some r's, multiply out, and we have 2 pi r squared plus, the r is going to go out, so we're going to have 2 times 128 is 256 times pi, all divided by r. So we now have an expression for our surface area where we just have one variable that is going to be differentiated. We'll go to the top of the page and work that problem out to the bottom. I'll be back in a moment. So picking up our problem with the cleared board and everything moved to the top, then we have this statement that the surface area is equal to 2 pi r squared plus 256 pi over r. This bit I'm going to rewrite as a power function to make it easier to differentiate. So now we're going to differentiate this. We're going to find out the differential of that. How much is the surface area going to change as we change r? And hopefully at some point we're going to arrive at a place where that goes to 0, and we know that we've reached a turning point, and that turning point we will see is going to be a minimum. So to differentiate this function here, 4 pi r, multiply out, drop the power down by 1, plus this, power is minus 1, comes in front, so that becomes minus 256 times pi, drop the power down, r to the minus 2. That is now minus 256 pi r to the minus 2. We can now tidy that up a little bit, okay, and say that what we've got is 4 pi r minus 256 pi divided by r squared, which is just the other way of writing that power there. We're going to set this equal to 0 because we're looking for the 0 point here. Okay, so the derivative there is that. Now we're going to make this equal to 0. 4 pi r minus 256 pi over r squared equals 0. And before we do actually that final step, we're going to put this lot over the same denominator here. Okay, we've still got to try and get r in one place. So let's make the denominator here r squared, which means you have to multiply the top by r squared as well. So what we've got is 4 pi r cubed over r squared. That looks a bit odd. Why are we keeping it like that? You're going to see in a moment. Minus 256 pi over r squared. And all of that is going to be equal to 0. Okay? So, we've got that equal to 0. If that is true, what we've got is that statement there. Let's move that all to there. If we want to simplify that, r squared goes to the top over here and it disappears because that's a 0 up there. And we're left with the statement that 4 pi r cubed minus 256 pi is equal to 0. 4 pi r cubed is equal to 256 pi. The pi is going to disappear on both sides. Okay. And we're going to be left with 4 r cubed equals 256. R cubed equals 64. R equals 4. And if we know that r is 4, we'll be able to put that back into our statement about what h is. We know that h is equal to, if I remember, 128 over r squared, which is 16. Therefore, h is going to be equal to 8 centimetres. So those are both in centimetres. And that's the answer to the problem. The height of the tin needs to be 8 centimetres and the radius of the tin needs to be 4 centimetres. Thank you.